Okay. Okay. Again, hello again. And we want to talk about field inside a uniformly charged sphere. I was saying that charges, so we're talking about a charge, but we also want to keep this general. It could be a gravitational field also. Charge could be positive, zero, or negative. And in this discussion, we will exclusively say it is all the charges I'm going to talk about is positive. And in that sense, that will have some analogy between gravity, because in gravity, we don't have zero and negative. So let's come back to positive charges. And they have this property that there is a flow. We can think of electric field, which is basically a flow of a physical quantity. Analogy is a flow of water. This is a source of this flow. And flow often represents a time-dependent quantity, but if it's continuously there, then it is pretty static scenario in that sense. So there is a Q here, and this electric field is to our understanding as of today, based on experimental observations, it is proportional to this charge Q, and it is inversely proportional to the distance, how far you are from it. So you're down there, its strength is 1 unit, and if you go twice the distance, it goes 1/4. So if this is 1, you double the radius, that becomes 1/4, and you double it again, and it becomes 1/16, let's say. So every time you double it, so it becomes square. So it's inverse square law potential. There's also a constant in between, which has the properties of vacuum in it. But for our purposes, that's just sitting there. It is going to be a spectator. We just want to think in terms of Q and R square. Left-hand side is a vector, so right-hand side should be a vector. So there is a direction associated with this electric field at every point. And for our purposes, it is radially outward. So this is a symbol which tells us that that's radially outward. That's all that means. So that's right. So that's a direction associated with that. So that's the simple idea. And we would like to now see the question we are asking is that what if you have a spherical shell which is having positively charged charges all uniformly distributed on it. So it's a spherical shell that has a radius r associated with it. And what will be the electric field inside the sphere? That's what we would like to motivate. And the answer turns out to be 0, right? Electric field is equal to 0. So first, let me give a very simple physical argument why that should be 0, and how this being 0 here will be a direct consequence of this 1/r square potential. Like one could ask in the very beginning, how are we so sure that it is 1/r square? Maybe it is, could it be that there is some other power law in there? And this being 0 is an immediate a consequence of that 1/r.
So you're saying that if we go to like if it's 1/r, we won't get this cancellation.
This cancellation, we will not get that exactly. Yeah. So that depends on this being exact 1/r square. And I'll motivate that in a minute. Like first, I will try to motivate that using just that symmetry arguments, or it's not even symmetry. I think it's a scaling argument I will use to show that electric field is 0. That's a standard thing. And then I want to do this, I want to actually build this by saying there are 2 charges, 3 charges, 4 charges, 5 charges, and I can build it, and in the limit, it goes to 0. So that's the 2 things I will show. So each one of them has a feature in it, and yeah, and while I'm building it using this 3, 4 charges, there I have some motivation, and I'll point out what it is as we are saying. The point is, what I want to say is that we have electric field has a source of it being charges, but once you have more than one charge, we can talk about points in space where we have the electric field going to 0, and those are usually saddle points. The electric field goes to 0 at particular point, but they all come in different directions. So that's an unstable point. But then one could ask, instead of talking about the charges as being the sources, can we think of those saddle points as being the sources and the charges as being just an effect? Like instead of saying saddle point is an effect and charges are the sources, we say saddle points are the sources and the charges are an effect. And that has this motivation that then we could represent vacuum in terms of that. Like when we think of vacuum, can we have a electric field distribution completely out of saddle points, no charges at all, right? And is that possible or not? So that's a very remote thought in the back of the mind, and this is all a warm up for that, just trying to fiddle around with it. That's what, yeah, since
Yeah, that's interesting. Yeah.
Yeah, so that's the idea, and this is all playing around for that purpose, if that makes sense. Yeah. Okay, so let me go back and say, so inside a spherical shell, electric field is 0. So let's motivate that. So we again take this spherical shell. So that's your sphere. So that's the center of the sphere. That's a positive. So there's equal distribution everywhere. This is uniformly charged, right? So it's important that it's uniformly charged. So charge per unit area is constant. So let's say we have a point somewhere, arbitrary point here. So that's your arbitrary point there, and that's where we want to calculate the electric field. And the moment you have that, I can draw a straight line, let's say like this. And let me also have another straight line passing through it. So I get a cone on the opposite ends of the sphere. This is, it seems like it is on the plane of a circle, but this should be thought of as a solid angle, right? This is a solid angle that it is making. Let's say the radius on this side of this infinitely tiny cone is R1, and the radius it forms on the other side is R2. And let's simply calculate the electric field due to the one side and on the other side, right? So let me calculate the magnitude. So magnitude of E1. So this will be the electric field due to the right side in here. So that's equal to 1 over 4 pi epsilon naught. And that is R1 square now. That's the electric field at that point from the right part of that code. And here you have dq1, right? Maybe I should say this is dE, right? So instead of electric field, so it's a tiny electric field dE1. So that's dq1. And immediately you say that this is uniformly charged. So the amount of charge that is on that surface is solid angle times the R1 square. So that's the key piece in here. So this is R1 square times the solid angle d omega 1. divided by 4 pi epsilon naught times R1 square. So since it is uniformly charged, there is a surface density of R1 square, so that cancels out. So that's equal to the omega 1 over what happened? And there should be a sigma 1, right?
Mhm.
The charge density, sigma 1. 4 pi epsilon naught. Same thing on the other side, it's immediate where we are heading with this. So this is dE2, that's equal to the omega 2.
I guess that you can clarify a little bit. dq is equal to sigma 1 r1 square d omega.
Yeah, how that works is that, so if it's a so what do we mean by uniformly charged sphere? That means charge per unit area for any piece out of this is constant, correct? So that means I can take the full sphere, that's charge q, that's it, divided by 4 pi capital R square, that's the radius of the sphere, right? That's one possibility. But I can, if it is uniformly charged sphere, I can pick any piece out of this and still have the same thing. So let's say this is sigma. And one possible area is this one. So I can pick any dq over, over the area. And the area here is the cone that is formed. So that is any r square times d omega. If I'm talking from this perspective, that's what it is. But even with respect to this, it is the same idea in that. So it is r square times d omega for any cone. So that's the area formed by a particular cone in that. So that's equal to sigma. Here, the area I'm talking about is the area spanned by this cone. And that is R1 square times d omega 1 times sigma 1. Sigma is a constant. So as far as sigma is constant, these two are the same. And d omega 1 is the same if I'm talking about opposite points on the cone. So for every point with respect to this point from here, the electric field will cancel the piece from the other side. And
d
since
omega is the angle that that area is putting, like subtending on the,
yes, a solid angle,
let's
correct?
say, three-dimensional angle, right?
Yes, exactly. Yeah.
Yeah.
So
That's why it is equal.
yeah, that's why. So this will be equal because d omega 1. So here
Opposite angles here.
yeah, d omega 1 is exactly equal to d omega 2 for these 2 points of that cone. But then I just have to talk about every cone I can scan around and they will cancel one after the other. And this will be equal to 0. So for every cone angle, DE1 will exactly balance DE2. So a simple symmetry argument, or more than symmetry, I think it's a scaling, right? Since there's an R1 square here and the surface density depends exactly on that R1 square, that R1 square canceling is what leads to this cancellation. And any 1 over R square potential and a corresponding R square dependence in the charge density will show this feature. Is that clear? Did I miss?
Yeah. So I guess, I mean, I was thinking, I mean, if you really want to have a different, oh, yeah, I guess, there are different configurations, but I mean, from like in this shell model, I guess if you consider like a different spatial dimension, you'll get a different power law, but then
Yes.
that will also, you'll get the same effect because then your DQ will come in with that same power.
As far as that sphere also is
Yes.
in the n-1
Mm-hmm.
geometry. Yes, correct. Yeah. Yeah, but suppose you say that the sphere is actually in
Plate.
3 dimensions and there is a higher dimension, then that will change this.
Yes. Oh, yes.
Then
Well,
that should
yeah,
show an effect in here.
exactly. Yeah, so if you consider, like, if this is just a circle, then in a three-dimensional world.
Yeah,
Okay, cool.
exactly. So in that sense, this will not be 0 if there were a higher dimension, correct? Or if the electric field was going into the higher dimension, and but our sphere actually is in 3 dimensions.
Mhm.
Right, so then that effect should show up. So the idea of Faraday cage working is a reasonable idea, that at least to some significant digits, because Faraday cage is only accurate to certain significant digits, I suppose, and in that, within that significant digits, we have we cannot have multiple or what is it, higher dimensional effects. Yeah. Okay, so that's so electric field is 0. So now we want to see this in a slightly different perspective. So let me go back to this point here. So we talked about electric field. I introduced the electric field. Let me also point out that this has this feature. This has this one more feature that I can put in any abstract volume, and if I search for how many lines are crossing the surface of that volume, it'll always comes out as the or it captures the source of this electric field. The idea is that these lines are always created by this positive charge. They will always originate in the positive charge. They will end in a negative charge unless they go to infinity. So at infinity, the idea is that there could be negative or positive charges. So that's usually that's the statement of Gauss's law. And what we're saying is that so capture all the electric field lines, all these lines of flow, right? If we can capture everything that is going on the surface, think of this as entities, catch all of them on the boundary of this volume, and that tells us the information about if there are any sources or not. If there is water leaking from the house, that means there must be a water source, a source of the leak somewhere. So that's the basic idea. And the right side in that way is whatever is contained in here. So that's Q. And again, for units purposes, there is an epsilon not in there. So let's, with this as a perspective, let us look into, let's just have 2 charges to begin with, and then we'll talk about 3 charges and so on. So let's have, I should change the camera, I suppose. So 2 charges is the simplest one. You have a positive charge here, positive charge here, and they're equal charges. Let's have that simplicity. So both are equal. And it is clear that right at the center, we should have the electric field equal to 0, whatever is the effect from that side, they should cancel this way. And if we give it some thought, it comes out to be electric field will always, for this configuration, will look like this. That's how it will be. And one can sort of have this feature that right at the center, the electric field goes in here. And from here, it goes in this side, right? That it should kind of have this feature that it seems 2 electric field is coming and crossing each other in a way. So here, actually, this looks like this. And I'll represent this as you approach this. It seems like at that point, the electric field should be that way. And at this point, this should be this way. And this is what we will call a saddle point. So it is stable from this direction, but it is unstable in the y direction. So that should be clear. And we often, that should also give a feeling for, we often say that the electric field lines should not intersect at a point. That's something that we see in textbooks a lot. But that's a point, that's a what do you say, a counter example to that. It seems like the field crossing. It comes out more drastically in 3 charges. So let's go to the 3 charges. This is, I think, the very little.
It is not exactly crossing, right? Like ideally, the fields will come as close as possible, and for a mathematical reality to the point, which doesn't have a dimension, but then it diverges from here in the upward or downward direction.
Correct.
So it is never that a straight line is probably never existing. It is like just always slightly diverging either upward or downward. And
but right on this line, there is an electric field, right? Right on this horizontal line, there is an electric field.
yeah, up to a point where there is no field.
Yeah, then it goes to 0. So in that sense,
Yeah.
it's
So in a way, like the lines that are going up and down also do not exist at that particular point. Like there is a tiny empty space in there, right?
not tiny. I mean, it's 0 empty space. Right? Yeah, I hear you, but I'm saying, yeah, it's kind of interesting. That's all I'm saying. Yeah.
Mhm.
Like I agree to what you're saying, correct? But it's not a tiny.
Like all you're
it's a
saying is
zero
that
space.
in that tiny empty space, if you keep a charge, it will be stable. But if you just nudge it a little bit,
Yeah, it's unstable, of course. It's
then it will
unstable
just
this way. Yeah.
go up. And if
Sure,
you
sure.
push it a left and right, it will try to come back
Yeah,
to the same
that's all
location.
I'm saying.
Yeah, yeah.
But let's keep this for the 3. It becomes sort of interesting, or one could make it interesting. Let's now say 3, right? So now I'm going to say 3 positive charges, and let me. How do I want to draw this? Yeah, I think I could. Yeah, and there's a symmetry I can keep. So let me think of. I'm imagining this to be on a circle. So that's one of the positive charges. And so this is on an equilateral triangle. So that's your 3 charges. And again, let us try to draw the electric field lines, and it should be clear that it will be something like this. And cylinder. And we could ask, there are how many points with electric field equal to 0, and surely we will, it's very clear that there is this point where the electric field is 0, right? Is that the center? Maybe slightly off. So that's your center, correct? And again, I can ask, what is the electric field here? That will be like this. Same idea as here. And one might wonder what is happening in there, right? And again, you would argue, yeah, okay, so that should be no surprise. It goes to 0, right? It is there, electric field is there on this line, but it almost goes to 0, correct? And now again, we should investigate, like you would like using the argument from here, you would like to say? Yeah, so how would you argue that? If maybe that's the point I can raise that. I mean, here, one way to think is that actually even a slight disturb, slightly off, is this what we are thinking or not? And the point is that that's not what is happening. Okay, so the electric field very close to this is not that way. So that's not correct. In fact, what is happening is that very close to that, it is actually going this way. So that's very counterintuitive. Okay. One can actually measure this, and this is like this. Is that
Then-
clear? Huh?
So you're saying that they cross, or?
They cross, yeah. And I
No,
can
they
make
should
it
not,
more
right?
real.
They should not cross.
They should not cross, yeah, exactly. But in fact, there it is worse, right? If I use Gauss's law here, all the lines are going in. Correct? So there should be a positive charge out there.
No, and then you are creating other possible places inside the sphere where there can be like electric field zero, right?
Exactly. So the point is, it's not that there is no one solution inside a 3-point charges. There are 4. It is 0 here, it is 0 here, it is 0 here. There are 4 points inside a sphere where 3 charges are on the extreme ends on a plane, on an equilateral triangle where it goes to 0. Okay. I can probably motivate this the following way. You would like me to show that algebraically a little bit?
Like, no, continue geometrically. Like, I mean, let's see what happens at 4.
Oh, 4, this will just be the same. But now, I mean, what one should ask is that this, I mean, immediately, at least I can mislead you guys that, oh, this must be wrong because all the field lines are going into the point, correct? Gauss's law is violated. There is no point charge there, right? So how does Gauss's law work? And that's where the point of saddle point is important. Actually, these on this plane, it seems like all the lines are going in. If you think of coming out of the plane, they are all coming out also. Is that clear?
Yeah, but that is what is bothering the way they are curving in. It's little hard to imagine how they are coming out without crossing. Like, even if they are coming out of the plane or into the plane.
Only on this plane it is going in. Completely out of that, it's all coming out of this.
No, but the point is, like, those lines also cannot end in there, right? Those lines have to come
Yes.
out.
They
And if
have
they-
to come out, even a tiny bit of you're off the plane and they will all come out. So they are very weak. Maybe I drew this so intense, so the number of lines.
Oh, so basically you are saying that those lines in the plane basically do not exist at all. Whenever the lines are so close,
yeah,
going
so
into
it
the
seems
center
like this
point,
is
they are
intense.
always off tilted the plane. Like, they
Correct.
start tilting off the plane right from the beginning, from the
Correct.
source itself, and then they go out.
Correct. Right.
It's still, like, I mean, the curvature, like, really, like the curving of those lines into is really.
Yeah, maybe I exaggerated this. I wanted to show that effect. So it seems like this is as intense as this. So I should draw less number of lines there. Yeah. But the point is that, yeah, field lines are going in there. And maybe I can show this more elaborately. So these are the 2 positive charges. That's right here. This is, and that's your center. So maybe this is how it is. Maybe this does a better job.
Yeah, but you don't want to end your lines there. Like, you have to somehow show that those
Yeah, but
lines
that's only one
come
line.
off the
If I
plane.
show many lines, then it's confusing. But at least one line is going into that.
So they wouldn't converge and into the plane?
They will, yeah, they are converging in here. Yes.
Yeah, but
they
in
are-
the other plane, the outward.
And they are going out. And here at this point, they are going like this.
Oh, so they're gonna
close
kind
to
of
a saddle point.
repel.
Yeah.
At once, okay. So you're gonna start coming in, even in the out of the page plane. They will,
I think this picture is still confusing. You don't
This-
want to end at the middle point.
Okay, how about this? Maybe, okay. This point here. Right?
yeah, but
Zoom in.
yeah.
I'm saying lines are coming in, right? I'm going to show it like this. Lines are going in. But in the plane, they are,
Shajesh, don't have a question that it is not coming out. All I'm saying is that those lines cannot even join at one location.
that's
Yeah,
it. I mean, see, what I'm trying to say is that there are two of the planes are coming in and this is coming out. The field lines, so that's what the saddle point is, right? There are lines coming in, coming out. So in this direction, they're coming out, and I mean, somewhere close to that. I have to show it somehow.
mhm,
So, like in this direction, they're going in or out, and in a plane, they're coming in. But this one is slightly different. Notice now this one. This is slightly different. We are saying that this way they come in, this way they go out. And they are coming out in the plane also. So here there are two lines that are going out, one line they are coming in. In two directions they are unstable, one they are stable, and this one is, so these two saddle points are different. That's my point. So this is a different kind of saddle point in the sense that two directions are stable, one direction is repulsive, or two attractive and one repulsive, right? If you want to say plus, right? I can say this is attractive, repulsive, and this is attractive, repulsive, right? In that sense, that's different, right? Those two saddle points, and we can see that in positive charges. So here there are two directions that is repulsive. So the between the two positive charges, we have two repulsive and one attractive. On the other hand, if it was one positive and one negative, not the one positive and one negative charge, how can I have the other effect? Yeah, I guess. Yeah, probably. I don't see it there in the positive charge here. I was wondering if that can be seen there itself. Yeah. But yeah, so this is fine. Main point I want to emphasize is that there are these 2 points, two kinds of saddle points that is there. One is at the center, and there are 3 of the kinds outside. Okay, with me?
mhm, yes.
And from this point on, I'm just going to generalize it. Okay, I'm just going to say, okay, so make this 4, right? If you make this 4 charges, it's again a positive charge here, positive charge here, positive charge here, positive charge here, and again at the center there will be a saddle point, and this point there will be 4 saddle points here. They're not really on the line connecting them, but they're relatively close. In this case, this is about 0.3 times the radius of that circle. So this gets closer and closer to that surface. So that's down here. So that's your 4 saddle points. And these lines are getting pushed away. In this case, less number of lines will go in towards the center. And one can see that as you increase the number of charges, this will get squeezed in. This points get outward, And in the extreme situation, there are a lot of saddle points on the outer circle, very close to the sphere, and there is a point, saddle point right at the center of the sphere. Did I motivate that sufficiently?
There cannot be a saddle point inside the sphere, right?
At the center, you mean?
Yeah, because for a sphere, like or even the complete up and down dimensions are pushing the lines in.
Oh, yeah, you're saying about a sphere, right? Yeah, I was thinking of a circle, right? I'm only telling.
Yeah, circle, if you keep the charges in a plane, yes.
Yeah,
There
yeah,
is a saddle point because into the plane and out of the plane directions are
correct,
open.
correct. Yeah. So, yeah, I think I was completely not taking that into account, right? So this is, I'm all talking about a circle. So yeah, so this is a cylinder in a sense, or circular charge. Yeah. So the only thing I'm talking about here is, yeah. So this is just this. Yeah. So
The charge distribution you're putting right now is in the plane
yeah,
of the
yeah.
board.
So I was overdoing it. Yeah, I was overdoing it. Yeah. Completely accepted. Yeah. So we are only telling this. Yeah. The only conclusion I'm making in here. Yeah. For a circular charge distribution, so there will be a saddle point right here, and there will be, in principle, in the extreme limit n going to infinity, there is a circular saddle point right hugging the circular set of charges. Yeah, my bad. Yeah, completely bad that I was taking it to a sphere. Yeah, for a sphere it will be completely different. Yeah, I agree. The geometry is hard to close on itself. Yeah. Saddle
Like
point.
maybe that is a point also inside that field cannot go stay inside a sphere.
Correct. Yeah. So yeah, I agree. It is a very, like, the moment you close it, then it's hard, right? Then how do you capture those lines? Right. Yeah, I completely agree. Yeah. I was getting carried away with that whole statement. Yeah, completely agree. But yeah. So overall, then at least my hope is that, or a thought is that, can we write Maxwell's first equation, like Gauss's law, in terms of these saddle points specify the electric field precisely enough? Like, it's like an analytic function. The poles determine your function completely, correct, in an analytic function. And similarly, in an electric field, do the saddle points somehow specify your electric field completely or not? So that's the thought. I wouldn't even say it's a well-posed question. It's just a thought. Yeah, that's all. Yeah, and I accept that I was carrying it too far, that I made it a sphere. No, not correct. But yeah, that's all I have. Yeah.
So can you keep, I mean, can you calculate the surface? I mean, this kind of saddle point surface.
Saddle point surface, you mean, or this point, right? You mean for
Like he
theta?
means to say that curvature of like saddle points, I think, right? That's what
Yeah.
you.
Yeah, so what it turns out is that very close to this, they will all have this x square plus y square structure. Like saddle point, always in the very close region, they will always have this x square plus y square minus z square, right? The metric, there will be this hyperbolic feature there. So yes, that surface can be in that close region, if that's what you mean. Not exact also you can get it, but in a very close region you will get that, you can capture that. Yes, so the answer is yes. So I plotted these things, I just for fun. You can see this more clearly in a, yeah, maybe I can show that, right? Maybe that might be since I did not derive that analytic expression, right? So I can show this feature in Mathematica. So I opened that so that in case, so this is kind of nice. Can you see this Mathematica
Yeah,
file? Where is it? Yeah.
yeah, we could see it.
Yeah. So
Okay.
that's how it looks like. So if you see, oh, this is in 2 dimensions, by the way. So this is in 2 dimensions. So that means this is a line charge at this point. And you see that there is only one point where it goes to 0. Okay, that's the center point. Okay, so for 2 dimensions, it's all
Not line charge. It is 3 charges in plane.
in a plane, but each of these charge is a line charge that's coming out of the board.
Oh, you said it is basically a wire coming out.
Yeah,
in
a
way.
wire.
Like
Yeah,
you can think that charges are distributed on a
correct,
wire.
correct. So that's one way of looking at it as 2 dimensions, correct? So,
Mhm.
but now let's say, now we go to 3 dimensions. So this is a 3-dimensional situation. And now you see that, you see this feature in here. So there is these lines going away here a little bit. So here they are coming in. So that's what I was showing, that they are coming in. Like maybe my
Mhm.
diagram was not good. So I can zoom in there.
Yeah, but Shash, see, they seem to be coming in from one charge. They seem to be going out. Like
No.
if no. If you look at the lines from the other 2 charges,
Mhm.
oh, they are also curving in.
It's symmetry, right? I can show a zoomed in version here.
I somehow don't like this image. I don't know. Like
But
it's
that's
kind
what
of
it is. I mean, the main idea is that when you have a 3 dimensions and you say that they are all positively charged, how do you make them go away? Like there is nowhere they can end. So they have to go to infinity. It's like combing your hair, right? Combing your hair without that point circular thing. Yeah, you cannot escape that. Like there is a theorem, right, in mathematics that you cannot comb a hair without that curl. And there somewhere or the other, you will have to have a curl in your head, at least one place. So similarly, I mean, if electric field has to originate, they have to go out. They cannot end in.
I don't have the issue of going out in the out of the plane. All I'm worrying is that even those lines that seemingly are ending in that point, whenever they turn and go out, because of their curvature, how are they not going to cross when they're coming out of the plane?
Like they'll come out of the board, right? And one will come go in and one will come out, and they will turn. Yes.
Yeah, I guess maybe at that exact.
Like once you bring in the 3rd dimension, I don't see any difficulty. It's like a cone, right? If I were to think of it as a plot, contour plot, it'll come out as a big pillar. Like maybe this one helps, probably not. Yeah, I think this is the best I have. And maybe, yeah, here is how it looks like.
Is it possible to draw these images in 3D? Or not possible, most likely.
Maybe a revolution plot, maybe. Yeah, it should be possible, yes. So maybe plot 3D, right? Let's see.
Is there a contour plot 3D also? But that will not work with just, I don't know, 2 parameter or something. You might have to include your Z direction also, right?
Yeah, here you go. So this is how it is.
I think this is just.
No, this doesn't tell you.
Can you do it the ones with, can you do the line?
Because you are just working with X and Y, right? This is different, Like this is giving a function of just that plane value. What is the value of the or magnitude of the field at that point?
Yeah. Correct.
I think you want to, if you want to do it, you have to include your z direction also. And if there is a way to plot those three.
Does this work like this? No.
We can try that later because most likely your V3 is not defined, well defined probably. You can go up and see how you have defined your V3.
V3 is defined, well defined, right? That's a potential in 3 dimensions, I suppose. Like, I don't remember the commands for revolution 3D, that's all.
You can do a question. Probably it's not 3D. It's just revolution plot, or I don't know.
Yeah.
You can put a question mark and ask like the parameters that goes on. A question, basically, in front. No, in the front, like before that.
FT, there's only 2 variables then. Okay, so then I should put it as 0. X, Y, 0. No, you want the Z, right? I thought, yeah, revolution plot 3T plots the surface.
So there should be a parameter.
Yeah, it's okay. I don't know.
Yeah, don't worry about this one. I think it's
Because we did do this for the other potential, right? That's another thing, that there is a lot of similarity between this saddle point and the saddle point in John's potentials, right? Like whatever potential you have in Casimir Polder, like all those points will have very similar structures. And they're very close to that point, they will all have the same idea. So yeah, we'll see. But yeah, that's the main. Yeah, I think this diagram has this feature. Maybe here. Yeah. So that's one, and these ones are. Okay, so that's all, I suppose.
So have you thought about the because at these saddle points you'll only have vacuum fluctuations, and then like this vacuum fluctuations at a single point.
Yeah, I haven't reached there so much, but that's a thought that, yeah, I mean, can we connect this with that? Yeah, like the best thing is that I think me and Prachi were talking is that, can we have a situation where we have no charges at all in this universe, only saddle points? So we will have electric field though. Like there are lots of saddle points plus and minus, so they all originate and end in a saddle point. So can we have a lattice of saddle points, no charges, but have an electric field in that tiny region? That will be interesting. Is that clear what I mean?
Yeah, but then you could ask what source is the saddle points then.
Yeah. And more than that, we started building. I think the idea was that, can we build such structure at all? Is it even reasonable to say that you can you finish and end? And I started it, but then I gave up in between.
Yeah, because I mean, I think these come out of just solutions to Maxwell's equation.
Correct.
So yeah, how would you get the saddle points without introducing charges in the first place? Like, how are you going to put in by hand the saddle points?
Yeah, I don't know. Yeah. Like they are surely.
I think the way
solutions.
one could ask this, repose this question, John, is that, like you can draw your system's boundary anywhere you want, right? And what if you draw your system's boundary right inside the charge distribution? Then you do not have any information of the charges. If you're just observing
See,
the
yeah.
field inside, then you will observe the saddle points.
Mhm.
Of course, I mean, everybody knows that, I mean, field
Yeah.
originate because of the charges. So that's a background knowledge, but
Yeah.
in the isolated system, this is not isolated anymore, right? It is
Yeah,
interacting with the environment. Yeah.
So yeah, can you find out information about the charges based on,
Charges, like what is actually creating the saddle points just by looking at the saddle points.
yeah, and see if that like information is different than if you like just enclose, like if you enclose these 4 saddle points compared to if you enclose the 1 saddle point.
Like the way to answer your question would be that, yes, for example, if you have 3 charges, I have 3 saddle points. So it seems like, yeah, if you don't have charges, then you don't have saddle points. But think of this as a periodic system, like a gyroid, for example, is an example. Like you need a boundary for a soap film to exist, correct?
Mhm.
But then if one cell of a system can support the next one, then maybe we can get rid of this boundary completely and move it to infinity in a sense. So some periodic effect might, does such a solution exist in the Maxwell's equation, that where there is only, there's lots of saddle points, but 2 kinds of saddle points, right? One saddle point kinds of balances the other. And can we have a lattice of that and have a solution where all the positive charges are, or all the charges are at infinity? And that might be a description of vacuum. So that's my very vague, intuitive, or maybe wrong thought.
So it would depend on the shape, because I mean, when if you keep a sphere, then you would have
Maybe.
like 1 round
Yeah.
saddle point. So
Yeah.
yeah, I don't know, maybe, well, if you keep it a lot, then you'll still have like that ring of saddle points, and then yeah, and one in
Yeah,
this.
those are questions I cannot answer at this point. Yeah, maybe there are effects of that boundary. Maybe that, how do you take care of that boundary? Like,
Yeah, you could
Yeah.
change.
Yeah.
Because how about for, there's like that square or rectangle configuration with the charges. How many, there's still 4 saddle points, and that's
Yeah,
a,
there will be 4 saddle points plus the 1 center. So
and
4 plus
there,
1.
yeah. Okay,
So kind of
yeah.
interesting. Yeah.
So a random question here.
Mhm.
We draw closed Gauss's surface around a charge, or like any position in space, to show whether there exists a charge or doesn't exist a charge there,
Mhm.
right? And the argument against drawing a Gauss's surface at infinity will be that you cannot close the Gauss's surface. Is that the point?
I didn't understand the question. Can you repeat it? So you want the surface to be at infinity? Gauss's surface?
No, not Gauss's surface to be at infinity. Like I can draw a closed Gauss's surface anywhere in space, right?
Yes.
I can draw it anywhere in space, and it will just tell me the right hand side of that, or just looking at the flux there, net flux of the electric field there, whether there exists a net charge there or doesn't exist a net charge, right? Like, I mean, if that is 0 or something, right? Now, if I'm just asking, like, I cannot think of drawing a Gauss's surface at infinity because I cannot enclose it. Because if I can enclose it, then it is not infinity. Is
Yeah.
that the point? Right?
Yeah.
Because why wouldn't somebody say that there is an infinite amount of charge sitting at infinity,
Oh,
or the sink, basically, like sink or negative charges?
yeah, but infinity is not part of our space, right? So that's outside. Right? So I think that's the best way to say it, that infinity is
So
not.
in that sense, like I can,
Mm.
your different types of saddle points in the triangular geometry, I can say that there always exist a tiny radius epsilon or delta, which I can draw a closed Gaussian surface, and the right hand side of that is 0.
Yes, it has to be.
I have to say it, right?
Yeah, saddle points, that is 0. Yeah, yeah, correct.
Yeah, it doesn't matter which type of saddle point you're talking about, like the middle one or the
Yeah,
outer one.
yeah.
Is there a connection between the number of saddle points that will occur?
I expect there will be. Yeah. Expect there will be.
So why is that? Like maybe I'm wrong, but in place of the 4 charges, it seemed like there will be 5 of them.
4 plus 1, yeah.
4 plus 1. Then why in the case of 2 charges, there seem to be only 1?
So 2 is 3 is 3 plus 1. 2 probably, good point. I don't know. Yeah, good point. Oh, what are you saying?
Because it's 1 dimension only? No, I don't know. I'm not
Yeah,
sure.
what happens to this
Oh, yeah.
pattern right when it is 2, right? That's your point.
Yeah, so it's like the behavior changes when you have more
Yeah,
than,
so below 3, right?
yeah.
Yeah, 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 yeah.
Well, and for 1 charge, it's 0. And then for 2 charges, it's 1. And then,
Yeah, that pattern begins at 3, kind of. Yeah.
yeah. So having 3 saddle points.
So
Yeah.
maybe the point is saddle points begin to exist only for 3, kind of, or 2 or 3.
I
There
think,
at 2 it begins, but then this pattern, yeah, I don't know. Yeah, that's good point. Yeah. So what happens to the, yeah, there. Or 2 gives you enough room to get the lines out, I suppose. In 3 dimensions, 2 is, yeah, so the number of charges has to be equal to the dimension of space, I suppose, to put in some constraints on where. Not sure. I don't know.
Yeah. Okay, good. I
Yeah.
think we can.
Yeah, let's. Yeah, good. Thanks. Yeah. So at least let me stop the recording. How do you stop the recording?